Imagine you have a big bucket of standard Lego bricks. If you snap them together one way, you might build a really cool spaceship. But if you take those exact same bricks without adding or removing a single piece and just snap them together differently, you might end up with a submarine. It's the exact same building blocks, but completely different structures, right? And they have completely different functions in the real world. Well, welcome to the wildly fascinating world of organic chemistry. I'm your host, and in today's Explainer, we're going to look at how molecules do this exact same thing. We are exploring the taxonomy of molecules, specifically demystifying a little phenomenon called isomerism. Let's dive in.
So, to establish our baseline, before we start branching out into the really wild rules of molecular structure, we kind of need a formal definition. Isomerism occurs when compounds have the exact same molecular formula. That means they have the identical number of carbon, hydrogen, or oxygen atoms, but they possess fundamentally different structures or spatial arrangements. Basically, they look exactly the same on paper, but they are completely different in physical space. The crucial takeaway here is that a molecular formula all by itself doesn't actually tell you the whole story of what a chemical is or how it's going to behave.
And this idea brilliantly illustrates our very first structural divergence, which is ring-chain isomerism. Take a molecule with the formula C3H6. On one hand, you can have propene, which forms this open, straight chain with a double bond. But on the other hand, those exact same 3 carbon and 6 hydrogen atoms can snap into a completely closed geometric triangle called cyclopropane. One is a flexible chain, the other is a rigid ring. Same exact pieces, entirely different architectural builds.
To guide us through this complex taxonomy tree, here's our quick roadmap for today. First, rings, chains, and tautomers. Second, stereoisomerism. Third, geometrical E and Z isomers. Fourth, optical isomerism and chirality. Fifth, symmetry and enantiomers. And finally, number 6, calculating total isomers.
All right, let's jump right into part 1, rings, chains, and tautomers, where we look at dynamic structural shifts.
What's truly mind-blowing here is that some molecules are literally shape-shifting in real time. We call this keto-enol tautomerism. Imagine a dynamic shift where a hydrogen atom actually migrates from a carbon atom over to an adjacent oxygen atom. It literally jumps across, turning what we call a keto form into an enol form. You might be wondering, why on earth do they do this? Well, it's usually to relieve electrostatic repulsion or to establish stabilizing intermolecular hydrogen bonds. The molecule is physically rearranging itself just to find a more comfortable, stable state.
Moving on to part 2, welcome to Stereoisomerism, where we officially enter the 3D world.
To really grasp 3D isomers, you have to understand a specific physical barrier. Visualize a carbon-carbon double bond. It consists of a standard sigma bond and a pi bond. Now, if it were just a single sigma bond, the two ends of the molecule could spin around freely, kind of like a wheel spinning on an axle. But that pi bond sitting above and below the plane, it acts like a physical lock. It completely restricts rotation. You literally cannot twist the molecule without breaking that bond, which takes a massive amount of energy. Because of this restricted rotation, atoms get permanently locked into distinct shapes, creating what we call cis and trans geometrical isomers.
So why does this matter? Well, these rigid shapes result in drastically different physical properties in the real world. A trans isomer has its bulky groups locked on opposite sides. This actually allows for really highly symmetrical packing in a crystal lattice. Think of perfectly stacked Tetris blocks. That super efficient packing means trans isomers generally have a much higher melting point than cis isomers. However, the cis isomer has its groups crowded on the same side, which creates higher polarity and a higher net dipole moment. Because of that stronger polarity and those sticky intermolecular forces, cis isomers typically boast a higher boiling point than their trans counterparts.
Okay, part 3, geometrical isomers, specifically the E and Z system. This goes beyond just cis and trans. What happens when those simple cis and trans labels just completely fail us because we're looking at 4 entirely different substituents attached to the bond? We need a universal tiebreaker tool. Enter the Kahn-Ingold Prelog or CIP sequence rules. It's like a game. Step 1. Assign priority to the atoms directly attached to the double bond based on their atomic number. The heavier atomic number wins. Step 2. If there's a tie, compare isotopes. Again, heavier mass wins. Step 3. Treat double and triple bonds as if the carbon is attached to 2 or 3 of those single atoms. Finally, step 4. If your 2 highest priority groups end up locked on the same side, it gets the configuration Z, which comes from the German word zusammen, meaning together. If they're on opposite sides, it gets an E, from entgegen, meaning opposite.
Let's actually apply those steps right now to a molecule like 2-butene.
Look at the carbon atoms on the double bond and compare the attached groups for each one. A carbon atom from a methyl group has a higher atomic number than just a simple single hydrogen atom, so the methyl groups get priority 1 and the hydrogens get priority 2. On one version of the molecule, both of those priority 1 methyl groups are locked on the exact same side of the double bond. That's our Z isomer. On the other version, the priority 1 groups are locked on opposite sides, so that's our E isomer. It's an incredibly logical, foolproof little system.
That brings us to part 4, optical isomerism and chirality, the invisible trait.
We're now looking at isomers that are identical in almost every single physical property, except for one completely invisible, utterly fascinating trait. To actually see it, scientists use a really cool instrument called a polarimeter. We start with unpolarized light, meaning its waves vibrate in every which way. We pass it through a nickel prism, which acts basically like a picket fence. It only lets light through that vibrates in a single vertical plane. This is plane polarized light. Then we shoot that perfectly flat light through a glass tube containing a solution of our isomer. And here is the absolute magic of it. When the light exits the tube, the plane of the light has actually physically twisted. The molecule itself rotates the light. No way, right?
And the direction of that twist is exactly how we categorize these molecules. If the substance rotates the plane polarized light towards the right in a clockwise direction, we call it dextrorotatory. We represent that with a small d or a plus sign. Conversely, if it rotates the light towards the left, anti-clockwise, we call it levorotatory, represented by a small l or a minus sign. It's a very subtle optical activity, but it reveals a profound geometric truth about the structure of that molecule.
Which perfectly tees up part 5, symmetry and enantiomers. Let's talk about the handedness of atoms.
So why do these molecules rotate light at all? It all comes down to something called handedness. It's exactly like how your left and right hands are non-superimposable mirror images of each other. In chemistry, we call these enantiomers. Now, this optical activity requires very specific conditions. Primarily, it heavily relies on having an asymmetric or chiral carbon center. Imagine a central carbon atom that is attached to 4 entirely different atoms or groups, say a chlorine, a hydrogen, a fluorine, and a bromine. Because all 4 things are different, there's absolutely no plane of symmetry possible. This asymmetry, this chirality, is the physical engine that twists that polarized light.
But hold on, because here is a massive plot twist in stereochemistry. There is a specific type of molecule called a meso compound. Meso compounds absolutely break the standard assumption we just talked about. Why? Because they do possess chiral carbon centers, but they remain completely optically inactive. They will not twist the light at all. How is that possible? Well, it's because they end up canceling out their own optical activity.
Take a look at a molecule like mesotartaric acid, for example. It has 2 perfectly valid chiral carbon centers. However, if you look right down the middle of the molecule, there is an exact internal plane of symmetry. The top half is a perfect mirror image of the bottom half. So, while the top half might try its hardest to rotate the light to the right, the bottom half rotates it right back to the left by the exact same amount. We call this internal compensation. The net result? Zero optical activity, despite being packed with chiral centers. Nature is wild like that.
Finally, part 6, calculating total isomers, making mathematical sense of the order.
We've seen a ton of molecular chaos today, right? Rings snapping shut, double bonds locking in place, invisible light twisting. But there is a beautifully mathematical, measurable order to all of this. We can actually calculate the exact number of possible isomers a compound can form. It all hinges on n, which is the number of asymmetric carbon atoms and whether the terminal groups at the ends of the molecule are the same or different. If the ends are different, the math is delightfully straightforward. The number of optically active isomers is just 2 to the power of n. But if the terminal groups are the same, that internal symmetry we just talked about comes into play. The math splits into a logic tree depending on whether n is even or odd. This lets us precisely calculate the active forms, those inactive mesoforms, and even racemic mixtures. It's a wonderfully elegant mathematical conclusion to all this 3D spatial geometry.
So, we've seen how molecules built with the exact same pieces can form flexible chains, rigid rings, locked geometric shapes, and left or right-handed mirror images. I want to leave you with this final, provocative thought. If 2 enantiomers are identical in almost every single physical way, existing just as non-superimposable mirror images of each other, how might our highly specialized 3D biological receptors react to them?
Could a molecule's simple-handedness really mean the difference between a life-saving medicine and a deadly, dangerous toxin once it enters the human body? The answer is, it absolutely can, and it absolutely does. But hey, that is a whole different topic for another explainer. Thank you so much for joining me today. Keep asking questions and keep exploring.